This question is from GATE 2019 Mechanical Engineering paper of set 2. The question is, one-dimensional steady-state heat conduction take place through a solid whose cross-sectional area varies linearly in the direction of heat transfer. Assume there is no heat generation, so it's very important that there is no heat generation in the solid and the thermal conductivity of the material is constant and independent of temperature. The temperature distribution in the solid is, so we need to find the temperature distribution in the solid, whether it is linear or logarithmic or quadratic or exponential. Now the one dimension steady state heat conduction equation with no heat generation can be written as is given by d upon dt of negative k multiplied by a to change in temperature with respect to x direction, because we are taking only in one direction. 1D steady state heat conduction equation we need to write. Now here in this equation, K is the thermal conductivity of the material, A is the cross sectional area, or we can also say that A is the surface area, T is the temperature. So dt upon dx is the change of temperature in the x direction, and this whole quantity is changing with respect to time. Now it's also given in the question that the cross-sectional area varies linearly in the direction of heat transfer. So let's understand this, what it's trying to say. Suppose this is the x direction and this is y direction, and the area varies from this point. Suppose this is section 1, this is, let's say 1, this is section 2, this is section 3, this is section 4, and it's given the area varies in the direction of heat flow and that variation is linear. But we don't know whether it is increasing or decreasing, but it is linear. Since the variation is linear, we can write cross-sectional area as some constant c multiplied by x, because the variation in the x direction is linear, plus some constant b. B can be said as intercept, and b is also area, that can be said that initial area. Suppose the area at section 1 is b, so a is the variation of area throughout 2, 3 and throughout the section 2, 3 and 4. Let our first equation be equation number 1 and the second equation of area be equation number 2, where this is linear variation of area. Now this is where you can pause the video. Using the given information in the problem and the concept explained here, you can try to solve this problem by yourself. If you need any help further, obviously you can resume the video. Let's continue our solution. So first let's substitute the equation number 1, that is variation of area, in heat equation, that is variation of area in 1D steady state conduction equation. So we can write d upon dt of minus k, and instead of a we can write cx plus b into dt by dx, and this should be equal to 0. So from equation number 1 we can write d upon dt of negative ka dt upon dx, that is equal to 0. Now if we integrate this equation both side, we can write, if we integrate suppose both side, we can write this equation can be written as negative ka dt upon dx should be equal to some constant, let's say c1. Upon rearranging this equation, we can write dt is equal to negative c1 upon ka into dx. Now we shall integrate this equation. So if I put an integral sign like this, so what will be the limit of integration? Let's see here. Now if you observe this material at point 1 and at section 1 and at section 4, so the variation of area is linear. So let's draw a graph something like this. Now this equation is A is equal to Cx plus B. Now this point is B and this is area and this is x. So variation of area with respect to x. And this is the B is the intercept on area axis. Now suppose this is section 1 and this is section 4. Now at this point, now what we need to do, if we are integrating, so the temperature at section 1 will be T1 and temperature at section 4 will be T4, and about x at section 1 it can be written as x1 and at section 4 it can be written as x4. Okay, so now let's put the limit here. So temperature will vary from T1 to temperature as T4, from T1 to T4, and the x axis variation in x direction is from x1 to x4. Now if we integrate this equation with the given limits, what we will get, the left hand side will be T4 minus T1, that will be equal to negative, C1 is a constant, K is also a constant, but area A varies linearly. So we can take C1 and K outside and we can integrate from x1 to x4. Thus dx upon the area is Cx plus B. Right? Now this can also be written as negative C1 upon K. Now this integral will become ln Cx plus B divided by C. So we can write C here, and from limit x1 to x4. See, x1 and x1 x4 or t1 t4 is just for a reference. Now again this can be written as, this equation we can write it as negative of C1 upon K into C, because C is a constant, and we will now put the limit, so we will get ln Cx4 plus B divided by Cx1 plus B, right? And this is T4 minus T1, which is the required equation. Now clearly we can see here the temperature distribution in the solid is logarithmic. So now let's match with the given options. So we see here option C is the correct answer. To get more information on one-dimensional steady state heat conduction, you can follow the NPTEL course on conduction and radiation by Professor C. Balaji of the Department of Mechanical Engineering, IIT Madras. Hopefully I was able to clear your doubt. Have a great day. Thank you.